Exactly.
Yes.
So welcome. This week we have Brand Gashes from Chalmers, and we look forward to talk. Brand, please go ahead.
Yeah, thanks for having me come and give a talk. Today I'll be just giving a kind of a broad talk in general about cosmic ray astrochemistry, in particular focusing on what really are the roles of cosmic rays in chemistry. I'll also start with what are cosmic rays, and some new tools that I have developed and that are around to try and improve our modeling of cosmic rays in astrochemical codes. So to start with, let me see if I can, there we go. What are cosmic rays? So cosmic rays are, generally they're just energetic charged particles. And by energetic, depends on then who you talk to. Where you can either go from these kind of, if you look on the right, this is a spectrum of, for instance, hydrogen and helium cosmic rays. We have going out to 10 to the 14 eV, all the way down, in this case, down to 10 to the 6 eV. So at MeV scales, and I say energetic. Some papers say it has to be relativistic, but for a proton at 10 to the 6, that's still very energetic, but it's not quite relativistic yet. On the left, this is actually just showing what the composition of cosmic rays are measured, and you see also compared to the solar systems, the kind of different abundance patterns in solar system, and this actually tells us where cosmic rays are formed, some of the physics within the galaxies. And in particular, you see that some different elements are enhanced by cosmic rays, like boron, and this kind of tells you about the physics of cosmic rays as they're going through the gas and the interstellar medium. Today, I'm going to focus pretty much on just the hydrogen and electrons, which aren't on this, but they are, of course, energetic and they are charged. We know, though, that at least cosmic rays exist, especially protons, also because they emit gamma rays. So when a cosmic ray, in this case a proton, interacts with some other form of gas, here also shown as a proton, it creates a pion, a neutral pion, in fact, and that neutral pion decays pretty quickly into gamma rays. And what I've shown here, this is the Fermi, I think, 10-year map of gamma rays, and you see that there's a lot of gamma emission at the galactic plane because there's a lot of density. And in fact, historically, some very early measurements of the masses of dense clouds were actually done by looking at their gamma ray emission, because that directly probes the density. Although that's kind of fallen out of favor a bit because it's much harder to do that than using dust or something. So for cosmic ray protons, what I've shown here are two different measurements, one with the Voyager and one with the AMS, which probe different energies. And this is the Voyager, I think, as of a couple of years ago. So it's when it had potentially left the influence of the sun. And so at the top left here, this is just the spectrum here in the points, fitted with a model line as this dashed dot. This is kind of a model fit 2-power law for the Voyager spectrum. Sometimes it's called the low spectrum with this kind of fancy L. And then there's this other one, this solid line. This fits the high energy slope from AMS, but then tunes that low energy slope to try and match the diffuse gas measurements. And this is sometimes called the high spectrum, and I should showcase this because the high spectrum will be used in my work, but it's now these two models are being used more and more as kind of typical spectra.
Are you going to mention the overall ionization rate then with these two models?
Yes. So that's actually on the right. But for the left bottom, this is showing the differential contribution to H2 ionization for each spectrum. And really what it showcases is how important the hydrogen or protons are as a function of energy for ionizing H2. So you see for this high spectrum and even the low spectrum, it's kind of between 1 MeV to 100 MeV, maybe up to 1 GeV for the low spectrum. But it's mostly, these kind of lower energy protons. So then on the right, this is showing the H2 ionization rate as a function of H2 column density into clouds with a bunch of data that's been taken. Kind of, these are kind of generally point sources or kind of lines of sight through gas. You see that there's a lot of spread, but there's maybe kind of something that's going down. Although this figure here leaves out gas towards high mass star forming regions. So there's a few measurements, for instance, towards actual stars that are at much higher ionization rates, in fact, would be off the plane. So there's potentially some evolution when you have local star formation. But those three blue lines you see are for three different external spectral models, with the low and the high as the dashed dot and the dashed. So you see the high model basically splits right through the data. That's not a coincidence of physics. It was designed to do that, and that's why it's been used, because it kind of explains the data. So the actual definition of the ionization rate, for those who aren't familiar, it looks kind of scary, there's a lot of things, but basically you're integrating the spectrum times some ionization cross-section. So of course, then the better we know your ionization cross-section for some molecule, the better we know the ionization rate for that molecule. And so the first term there, that's for the primary particle, so the primary proton or electron from the interstellar medium. Then you have a bunch of other ones below it that are from induced particles, typically induced electrons. So you have a first generation induced ones, and then you basically have a whole cascade of electrons that can be induced. Most commonly, all of those terms are kind of ignored, and you just see it written down below where it's just in terms of the primary, and all of this induced physics is characterized in this phi term. And this has been kind of characterized from previous works throughout numerous decades that have kind of put this term somewhere, around 0.3, 0.5 or so. And just to kind of make some clarifications here, this is from this Padavani and Gaseous chapter, that when people talk about the cosmic ray ionization rate, there's actually three different ionization rates that are mentioned. Sometimes you'll see one labeled as zeta 2 or zeta H2. This is the H2 ionization rate, so the ionization rate of H2. Sometimes you'll see zeta 1 or zeta H. This is the ionization rate of atomic hydrogen. And then you'll see zeta P. So that the zeta 1 and 2 are the total ionization rates. The zeta P is just the primary ionization rate of hydrogen from protons. And so down here, there's some nice relationships that kind of tell you how to convert between them. But it's just worth noting, especially if you use cosmic rays for things, that this can lead to some whoopsies when you try and model something and you forget which one you're using. So I showed back here, this was kind of a lot of the state of the art as of 2021, 2022, when we made these plots for the ionization rate measurements, and they're just single points on a plot. Now, in fact, though, it's gotten good enough that we can actually make maps of the ionization rates. This is just from the past year alone, from Jaime Pineda, Giovanni Sabatini, and Victoria of the ionization rate within regions. And on the far right, this is actually towards a protostar, and you see the ionization rate that's inferred is actually going up to 10⁻13, 10⁻14. So I said that would actually be off that graph in the last one. So now we're going from just kind of single points on a graph to actually having maps of the ionization rate. And this allows us to do much better at trying to constrain the physics of it, because now we can actually look at what the spatial distribution is, instead of looking at points that are not in the same cloud.
Are you going to talk about how they make these maps?
I'll mention one of the ways that they measure, not this one before, the diffuse gas. But in general, the way they measure these is you basically take ratios of different molecule column densities, and using some analytic chemistry, then you can back out from, in an analytic sense, the ionization rate.
Aren't those ratios time dependent?
So it generally assumes steady state, but for some of the molecules, the chemistry is fast enough that it's normally seen okay, but not for all. So this is one of the caveats in trying to do better at trying to actually infer the ionization rate. But as cosmic rays travel through the gas, they lose energy. And so I've shown here, you can see just this top line. See if you can see this, not easily. Here we go. You see this top line, this is the energy loss function for protons. And what you really just want to take away from this is that they can lose energy quite fast, especially these low energy ones. This right here, this is the energy loss due to this pion by making pions. It starts at around 380 MeV. This peak is from ionizing hydrogen or H2, and this peak down here is from exciting vibrational states, for instance, of H2. But we know that they lose energy, and so as they travel through the clouds and they lose energy, they create complex ionization rates. And unfortunately, most studies still assume a universal constant ionization rate that is this low ionization rate, which, as you see, is actually sits below a lot of the data too. So we need to do better with that, and we can. So for the actual chemistry, what do cosmic rays do? So cosmic rays act really as ionization sources, and ionization is really important because the chemistry in clouds are so cold that the chemistry has to go through ion-neutral reactions to help initiate a lot of the chemistry. Because neutral-neutral reactions, trying to cram two neutral molecules together, oftentimes there's a barrier, and so you have to kind of bypass this barrier. But ion-neutral reactions typically don't have this. And so if you look at this, you see there's a huge kind of scattering of chemistry that happens from basically just ionizing, say, a few things, in particular, hydrogen and H2. But we can look at, so some of these different ones, and you can see one of the formation pathways for NH3 is here. Formation pathways for hydrocarbons and carbon chains kind of sits here. Gas phase water, mind you, this is for very diffuse gas regions. Most water, the ISM actually forms on dust grains. And this is one possible formation pathway. And I'll note really quickly this formation here to OH plus. This will show up a bit later, but you see it's just a couple steps. So it's actually very fast. And so OH plus, H2O plus, and H3O plus are oftentimes used to infer the ionization rate. The initiation of deuterium chemistry also goes through this from H3 plus. And H3 plus is in general a very big molecule because H3 plus interacts with basically everything and exchanges a proton and basically helps make things more complex. A few different things from carbon monoxide chemistry kind of goes through here. And I'll note that you'll see over here, carbon monoxide is actually over here too. Helium plus is probably the most important destroyer of carbon monoxide in dense gas. And you only get helium plus from cosmic rays. Now, going to this OH plus, this is one of the ways that the column density of OH plus is used to constrain the ionization rates in diffuse gas. So the hydrogen ionization rate, the kind of analytic formula is shown on the top left. And I show this because it really shows a new problem in astrochemistry. And that's we had a number of reaction rates that were either measured or calculated from the 90s or 80s that were thought to be robust and very good. And then people have since been going back to them and either recalculating them or remeasuring them and finding that there's significant changes. And sometimes this is due to new pathways that are able to be taken into account or better methods. But in this case, for instance, this is showing on the left, this is this dissociation recombination rate of OH plus shown on the top right. And the blue band is the new results from this the paper in 2023. And on the right, this is the multiplicative ratio of if you use the new rate versus the old. So you see in the kind of for low H2 gas, so when it's mostly when the hydrogen is mostly as H, the ionization rate that's inferred might actually be a factor of 5 or higher, greater than what was previously inferred. So this is a pretty simple though reaction rate that people thought was pretty robust. So it's a pretty interesting problem that when you go back and you reinvestigate older rates, you start to find surprises where things kind of didn't match up anymore, and it completely changes what we had inferred before.
You're saying the data you showed on the plot before, and it's all kind of...
Yeah, so in fact, there's also another one with the C2 is oftentimes used to measure the density to kind of help calibrate these. So most likely, these points will probably have to go up a little bit, and these points here, so actually the H ones are actually over here. These ones, and not on this plot because it's for H2. But the ones for H will probably have to go up, and these ones actually there's a new rate for C2 which measures the density. These will probably actually have to go down by a factor of 2 or 3. So these things are now starting to move around as we're starting to actually go back and relook at some of these rates. So furthermore, when a cosmic ray proton, for instance, ionizes H2, it ejects an electron, and this electron can then provide energy into the gas. So I've shown here on the right, this is just the temperature of the gas. It's a function of the gas density and the ionization rate. And if you focus in on the dense gas, so say density of say 10 to the 3 or higher, you see that the temperature is almost entirely determined by the ionization rate. So if you're in the dense gas regime, your ionization rate is crucial to determining your end gas temperature. So kind of as a kind of last thing to talk about for cosmic rays in the gas, when the H2 gets ionized, sometimes it can just get excited instead of ionized. and in which case then you get a decay down from the excited states and you get the generation of UV radiation. And in fact, cosmic ray induced UV radiation is probably the most important source of UV radiation in the densest gas away from stars and everything. So I'll kind of skip this because it's showcased here. For ice chemistry, there's been a number of laboratory measurements that have recently shown that if you irradiate different ice mixtures with lower energy electrons, you can actually stimulate the formation of complex molecules and carbon chains. So I've shown here the black on the left line shows basically what this absorbance spectrum was before there was any irradiation. And as you increase the irradiation, you see the enhancement of, for instance, methanol, but also these carbon chains here as well that are being driven by the chemistry. And even more exciting, if you look over here, this is from a mixture of CO2, CH4, and ammonia. When they irradiated the ice, you can look down here. Actually, this is for the mass spectrum of some species with the mass of 75, and this is formamide, if I remember right. But it's a prebiotic molecule. So you get complex chemistry basically driven from simple things when you irradiate the ices. Yeah, so this has now actually been measured also for sputtering, so knocking things off the grains. It's shown here on the left. This is from laboratory measurements, which have been included in astrochemical modeling. And just to kind of focus on the right, if you look at the black line, includes all sputtering, and in the dense gas, the red line is sputtering from cosmic rays. And what's really shown is that you need this cosmic ray sputtering to try to predict the gas phase abundance of methanol. In this case, this is for TMC1. But in this model, I've shown down here the equations. They assume basically a spectrum averaged rate for the yields of knocking things off the grains. But in fact, the laboratory data has it as a function of energy. So future astrochemical models could actually use cosmic ray spectrum instead of normalizing everything just by this rate and do a much better job at doing this. So finally, I just want to mention that, because we have to know about the cosmic rays, one of the big things that I've been doing looking at embedded sources of cosmic rays, you don't have to have hugely strong accelerators, like you don't have to do like an AGN or something where you're trying to get the PeV energies or above. You just need to get the KeV, MeV, maybe GeV energies. It turns out there's a lot of potential sources. And I'll just really note that, two of the ones I've worked on are in acceleration from turbulence and by protostars. But all of these models basically that have been done have assumed analytic theories for the acceleration, because when you start to model the theory of it, cosmic rays are accelerated by shocks and within instabilities. And unfortunately, once you start to resolve one instability, you start to see another instability. And so you work to resolve that instability, you start to see another instability. And basically, as you start to increase the resolution to hopefully you reach the end of it and you can start to explain things, you still get resolution, you still get instabilities. It's just instabilities all the way down. You can't really avoid it. Even at the smallest scales, if you go to like the full plasma scales, there's still instabilities. So no matter what, you're still
not necessarily giving shocks. I'm not trying to remember how.
Not always shocks, but still instabilities. So things like the gyro resonance instability would probably be the 10th or 11th turtle down there.
But I mean, the MRI and the disk, there's no shocks there, is there?
There's no shocks except there is turbulence. And so if cosmic rays can be accelerated via turbulence, then of course that can be it. But in general, the problem is whenever you try to resolve these things, you end up just constantly going from one instability down to another and hoping that you can finally get something settled. So I'll just kind of breeze through these next couple slides. They just show the observational evidence of cosmic ray acceleration through synchrotron emission in jets and synchrotron emission in H2 regions. So we know that these sources are accelerating at least electrons. But now we're going to shift back over to the chemistry. And this is really what I've been doing for the past couple of years, is doing 3D astrochemical modeling with a astrochemistry code that I have put in kind of more advanced calculations for the cosmic ray ionization rate. So instead of just using a constant ionization rate, you can do it in 3D. You can either use a given just functional form of the ionization rate as a function of column density, or you can actually just give it external spectra and it solves the energy loss equation for the spectrum as things go into the cloud. The models I'll show today used this prescribed function almost entirely because we didn't have the memory on the computer where this was run to store the spectra for everywhere. So we just used this this analytic. And what we did was we post-processed these 3D hydro simulations from Ben Wu. And this black line here, this is the prescription that is included in the code in 3D. So you have the column densities in 3D, so you get the ionization rates in 3D. So one of the first results you get from this is that you can look at the ionization rate as a function of density. And you see, of course, as you go to more dense gas, it's more deeply embedded, so your ionization rate drops. But you can also see that there's a significant amount of scatter within this. And this scatter, in fact, could be a physical explanation for the scatter that you see in the observations. That because the observations are doing line of sight densities, but that's very different than the effective, the line of sight column densities, and that's very different than the kind of effective column density of the attenuating gas. And so the spread that you see might actually just be a physical result rather than observational biases. But we can look at the impact of different assumptions on the cosmic ray physics on what we model for the column densities of C+, neutral carbon C, and CO. So I've shown you on the far left in the kind of dotted red box. These are the column densities using the attenuated cosmic ray model. And then in the colors, this is the relative error in the calculated column density if you assume different constant ionization rates throughout the whole cloud. And so if you look at, for instance, C+, if you go to too high, you end up overproducing C+ in the dense gas. If you go too low, you're underproducing it at kind of intermediate densities. But maybe 2 times 10 to the -16, it's just right. It looks like it's pretty white, it's pretty clear. But then you go one row down at neutral carbon, and it starts looking a little bit worse. It becomes you kind of in some places you're underpredicting, in other places you're overpredicting. So it's not just a constant fix. And if you go one row down to CO, well, in the dense gas, okay, CO will do what it does and just convert everything into CO. But in the diffuse and intermediate regimes, all of a sudden it becomes very significant depending on what you choose.
Has anyone mapped then the maps you showed of cosmic rays?
Yeah.
And correlated that with density?
Not that I know of. But that's a good question. I can actually ask Jaime and some of the others because I'll see them in a month and a half or so to see if they can do that. So this is for the column densities. We can look at it for the measured fluxes. So again, this is the same kind of plot, but instead of for column density for measured fluxes. And this is a little bit better. The relative errors are a bit less for CO, but for C+, really what you would assume really matters. We're talking about 50% relative errors if you go in order of magnitude each way. But maybe if you're only focusing on trying to get kind of order of magnitude or kind of factor of a few right on the emission, this kind of 2 times 10 to the -16 one seems so far to be doing the best. And it turns out that this is also about what is expected to be the kind of average Milky Way ionization rate as well. So one of the reasons why this ends up impacting things is not just from the chemistry, and that's from the column densities, but also from the temperatures. And so I've shown here, this is the temperature distribution of the dense gas, so only looking at gas with densities 10 to the 3 or higher. What you see is for this black line, this is the attenuated model. If you go to too high ionization rate, you end up overheating the dense gas. This, for instance, for C+, produces more emission. If you go too low, you're kind of okay. But the actual kind of, if you look at the very fine ones, this is actually why CO is a bit different, because this, a few Kelvin matters for the level populations in the dense gas. And so you end up having pretty different level populations in non-LTE, depending on basically if you have a few different Kelvin each way difference. To kind of put that all together, this is a three color image is of the attenuated, the 10 to the -16 ionization rate and the absolute difference. The top is for C+, C, and CO, and the bottom is for CO at different J levels. And the really key takeaway is if you look at the absolute difference, is that it's not just a constant shift between each level. You really see kind of a complex morphology where sometimes it's wrong in these kind of intermediate dense regions, sometimes it's in the dense regions or the diffuse. So if you're trying to model multiple species at once, you really have to kind of do it self-consistently with an attenuated ionization or just something more physical than a constant ionization rate. Basically, no constant ionization rate model can reproduce all 3 lines at once. So trying to measure the ionization rate is absolutely crucial. There's a new method that's been proposed by a colleague, where you have electrons interact with H2, and this pumps the vibrational states of H2. And this then induces infrared emission that James Webb, for instance, can't observe. So we have a proposal that was accepted for this. And the way the outcome of these models is quite simple. So from a 1D slab calculation, so Schmoil Bialy proposed this in 2020. Marco Padovani and them did a quick calculation in 1D with a much more sophisticated treatment of the electrons. And the way this works is if you can measure your flux of some line for the H2, you can measure the column density of H2, which you can do if you have multiple H2 lines. You have an inferred ionization rate shown here by the contours. So this is great. It's a completely chemistry independent way proposed, but we really wanted to test if this actually was chemistry independent. So we did this in 3D with both these submissions from Ben Wu and from Silk. So the Silk ones here look nicer just because they were done at high resolution.
So there's no rate of pumping.
So this method only really is purely sensitive to the cosmic rays in environments where you're away from UV sources and shocks. So the site that we're actually going to be testing it is B68. It's kind of out in the middle of nowhere, Bach globule. There's no really high UV radiation there, and so it's thought that then if this mechanism is valid, we should be able to see it there.
Long line of sight would be, I mean, some central region could be shielded, but along the line of sight there would be some gas that's not so shielded.
Yeah, so as long as the UV field isn't above, say, a G naught of like 1 or so, then or even a few, the cosmic rays will dominate. So Schmoil actually did this and tried to figure out at what levels of UV you can actually do this or not. But the key takeaway here is on the right, and that's that the Silk zoom and the 3D PDR measurements and these 1D models all kind of overlapped when we were trying to model for the same ionization rate. So basically that, how you actually do the chemical modeling. So all of these had different ways of solving the chemistry, but they all agree with each other. So this should be a relatively robust mechanism of doing this. So there's been a James Webb proposal that has been accepted. So hopefully we'll be able to see it. Further, for like high J lines, shown here on the left, on the right, is just showing the error of the high J lines. And you see that basically what you measure really matters for the high J lines. And so for the very high J lines, this could actually matter for FIR observatories. I've shown here the one that I'm on, only because it's a really cool logo. So to kind of finish up this section is just to have some cosmic ray implementation recommendations that we've kind of put together. And that's for the absolute best results, you should use a spectrum resolved cosmic ray transport solution. So far, there's only one code that has this, and this is 3D PDR, but it is public, so anyone can use it. If you don't do that, and if you only have, say, a local effective column density, you can just use a pre-computed column density ionization rate. If you only have a density, you could use an AV-NH relationship and then use the above relationship. If you can do none of that, for kind of cloud scale models, for instance, within the Milky Way, you can use this 2 × 10⁻16 or some other empirical value from, I'll say, current observational analysis. And I say current because this fiducial kind of 1 to 3 × 10⁻17 ionization rate is from observations, but it's tied back to observations from like the 70s. We've gotten better since then. And so, yeah, it's just better if you can't do any of these things to basically, look at what's been done in the past few years, because these things do change quite a bit. So onto some new tools. Recently, I initiated this Astrochemistry Low Energy Electron Cross-Section, or ALEX database. This is the largest database of its kind for ionization cross-sections. We have over 200 molecules and atoms. I think last I checked, it was 244 molecules where we have optimized the structures and the geometries at a few different levels of quantum theory. So we have the single ionization cross-sections and ionization rates, as well as in some nice chemical formulas. So I've shown here on the right, this is just a histogram of the population of how many atoms we have. One of the other, so for astrochemical modeling, it's adding an ionization process nice, but one of the other sources where this is really important is for laboratory work. If you do mass spectrometry and you want to compute, for instance, from the mass spectrometry data, your column density of gas that was in there, you need to know the ionization rate in order to calibrate this for that species. And so this is shown here. And I pulled this from a recent paper where they did some laboratory data. And you see the blue boxes are for molecules, and there's a little C next to it. And the C means that there was no measured or calculated cross-section for those species. And so they just had to assume something. And generally, they assume something based off of its being similar to something else. It's worth noting that the database now actually has some of those. So it's great. We can basically expand this for laboratory data to make sure the laboratory data can do as best as possible. We built a couple ways to access it that are still in development. So if anyone wants to help get involved, that really loves doing like GUIs or things like this, or database structuring, this is definitely a way in. And kind of going forward, we the group has a number of kind of planned or kind of hopeful upgrades. So one of them is to upgrade all the cross sections to their fully relativistic forms, to do kind of empirical singly differential ionization cross sections, kind of things of interest. These are things that we've kind of reached out to people who might be interested in doing it. Is to include excitation cross sections, either compiled from literature or computed. The computing means doing a fully quantum chemical thing. I myself can't do that, but we have people who are interested in the database who can do this. Doing dissociation cross sections, this is a little bit harder, but still viable. And one thing that's been kind of brought up in the past week or two, since I guess last Wednesday or so, is doing machine learning to try and predict cross sections for new molecules. So one of the ways that you can do this, for instance, is by mapping the molecules to a chemical space, basically, and then try to use some neural networks to do it. So this is, for instance, what mapping the subset of the database to a chemical vector space looks like, to try and see what the relationships between them all are. So there's some kind of cool things within kind of machine learning and chemical data analysis that can be done. For a lot of the different studies for cosmic ray interactions with grains, it's normally assumed that all of the energy of the particle that the particle loses as it's traveling through the grain is left as heat. But this has never actually been measured. And so future kind of calculations can do this better. So I've shown here on the left, this is a prototype setup with a particle physics code of a 2 GeV proton interacting with an icy grain. The red here are electrons, but what you see is that the electrons are a lot of the electrons are escaping the grain. So this 100% heating efficiency is clearly not valid if the secondary particles that are supposed to be dumping the energy are actually leaving the grain. And part of the reason why this is different than previous ones is previous ones generally they would do a simulation with like a cubic region of ice and kind of just shoot something through the ice. But a lot of the electrons, as you see, are injected within the mineral grain, not the ice. And so then these are kicked off with a lot higher energies and can then escape. In principle, the energy deposition is going to be put into a quantum chemistry calculation of the ice. So I've shown here, this is an example from 2017 of a different group that did this, where they've assumed a certain amount of heat in that track. But this was just an assumption. They didn't actually do this. They didn't actually know what it would be for that particle. So finally, there's new tools for including cosmic ray physics. So as I mentioned, the cosmic ray physics in 3D has been included into 3D PDR. Right now, what we do is we use the spectrum to compute the hydrogen and H2 ionization rates, but not for the other things. But now we have a whole database full of cross sections that we can actually do this with. So that's a possible future goal of the code, is to start to actually use this cosmic ray spectrum to do more things for the heating and ionization, which no other code can do. And to kind of include larger networks to try and investigate more of the different molecules which are used in inferring the ionization rate. Further, this module that does the spectrum computation has actually been included in Nautilus, which is a full gas grain code. And I've shown here, this is just an example of the ice composition as a function of column density into like a 1D slab. If you include cosmic ray attenuation or you don't, and if you squint very hard, you'll see that not only do the kind of size of the ices change mildly, but the composition of the grain itself is actually changing whether you include the cosmic ray attenuation or not. So I'll just leave up my conclusions and then for questions, because the conclusion basically cover everything I already just said.
Very good, thank you. So the time for questions and discussions. So raise your hands in Zoom or here or there.
This guy needs to speak up.
Jonathan, could I ask a quick question?
Please.
Hi, Brent. Nice talk. I had a question about when the slide where you show the different chemical reactions that are important for cosmic rays, in particular with CH3 plus. How important is cosmic ray ionization for driving CH3 plus? Because I know they haven't seen it much, outside of our solar system, and the only object where they saw that was towards a UV irradiated dominated source rather than one dominated by cosmic rays. So are other networks more important than that one?
Yeah, I mean, so this is not meant to be an exhaustive list of everything to do with these molecules. It's more so that these are in the different chains. So the CH3 plus is not formed from cosmic rays directly. It's just because you have one of the formation pathways to get that is through C plus. And one of the ways to get C plus, you can do it from UV ions from strong sources of FUV. But also if you dissociate CO or other things with something like some other heavy ion, you can then produce C plus, for instance, or you can actually directly ionize C plus. So that's much more kind of subdominant. But that is just a way to produce C plus. For CH3 plus, there's probably other reasons why we haven't seen it also. In part just because the dissociation recombination rates are actually have been recomputed, and they've been found to be different than what people have previously assumed also. So the chemistry for CH3 plus in the next few years might actually undergo some changes because of some new reaction rates that have done with it. But this is not meant to be an exhaustive list of like everything for each species.
Thanks.
Okay, other questions? You showed a graph of the temperature distribution
Yes.
and the impact of the attenuation of the cosmic rays.
Yeah, for the distribution.
So how are you doing the temperature? Two-part question. How exactly are you doing the temperature calculation here?
Yeah.
I mean, is it in 3D PDR? Do you have the necessary heating and cooling physics? And I'm generally interested in how we can use measurements of temperature to constrain cosmic rays. It must depend on also the efficiency of the cooling, which depends on the grain sizes.
Yeah, so in fact, I think it was Stefano Bovino had a possible mechanism of using temperature and I think one other molecule to constrain the ionization rate. Because in the dense gas, as long as you're away from embedded sources, the temperature is largely just a function of the cosmic rays. For 3D PDR, it does have pretty robust gas chemistry or in gas heating and cooling. So it computes basically all of the important rates for heating. And for the line cooling, it does a full non-LTE calculation as well with the line radiation escape from the clouds as well. So I'd say for 3D PDR, the heating and cooling is probably pretty robust. There's a few mechanisms, for instance, that doesn't actually include, but for clouds, those are normally really, really subdominant.
Dust cooling as well.
It has dust cooling as well, but again, it assumes things about the dust distribution and things like this.
You have nothing down to 10 Kelvin.
Yeah, I have nothing down to 10 Kelvin. So this has, I think, a UV field of, I think 4 drain. And so, yeah, but mind you, these are still relatively high ionization rates compared to, say, the kind of typical ionizers that are used of like 10 to the minus 13.
Okay.
Can I also add something here?
Thomas.
Yeah, so speaking on temperatures, of course, the high JCO lines are also another good indicator of the presence of cosmic rays, high cosmic ray energy densities at high densities, because high JCO lines are very, very sensitive to the gas temperature, and we can actually see the footprint or the signature of elevated sleds, CO sleds, as you have here, Brian, yes, on the left side. This is for XDR, as far as I remember. Yes, this is for X-rays, and on top is for PDR, but I would presume that for cosmic rays, you would have something similar with XDRs.
Cosmic rays are also on the right from the 3D models.
Oh, yes, yes, yes. So you can see the high JCO lines that It's another good indicator of the. I think Bradford was one of the first that proposed that a few
Mhm.
decades ago in galaxies. Yeah.
Well, I remember looking at high JCO lines in RDCs with the Herschel, that was Andy Pond's thesis.
Mm.
And you're comparing between PDR models and shock models.
Mhm.
But now you've got the cosmic ray axis as well.
Yeah, I'll note that. I mean, the actual literature for XDRs and cosmic rays is pretty slim. I mean, very few papers have actually looked at X-rays for XDRs. Most of the people who have looked at XDRs are really looking at the contributions for AGN, so they're doing much simpler modeling. And for cosmic rays, there's even fewer that have really done a lot of modeling for the high J lines and the kind of far infrared lines.
But can you really distinguish between shocks and cosmic rays and G naught?
My guess is you could probably, I mean, you can distinguish, for instance, between G naught and the X-rays by the ratios of the different lines. And so you see, I mean, the two models there on the left, the top and bottom are for the same density and the same column density. It's just the exciting source. And so you get very different line ratios and you get very different sleds. So presumably, you know, for CO, it would be pretty similar to that.
Also,
Or sorry,
dust
for
SEDs,
cosmic rays, it would be pretty similar.
Also, dust SEDs are important there. If you have high JCO sleds and also high dust SEDs, then it may be a result of FUV, presence of FUV radiation. But if you have a dust SED that corresponds to low FUV intensities, then you know that it's coming from cosmic rays or something that is not photons. Hitting.
That's why going to these pre-stellar cores or shielded, at least from the UV, is
Mhm.
good.
Yeah, so in my opinion, CO sleds and dust SEDs have to be treated in tandem, together. That would be a useful constraint.
Okay, any other questions?
Could I ask another question, Jonathan?
Yeah, please, I need help here.
Brent, could you go back to the slide where you're showing the temperatures and the models with the different cosmic ray ionization rates? Yeah, that either one of those two is fine. Yeah, so it looks like 10 to the minus 16. Is that the like fiducia value for the ISM? Because I know a lot in like disk chemical simulations, we use 10 to the minus 17 as the standard ISM value, or
Yeah.
weaker values if we consider attenuation through the wind. So are those values kind of outdated compared to what I'm seeing with your simulations, or not?
This would depend a lot on the region and the source. I mean, I think historically, people have used 10 to the minus 17 because it was deemed the kind of fiducial ionization rate. And there's a number of communities that have been hesitant to move away from that. Sometimes they invoke these types of plots for the ionization rate as a function of column density, because, you know, and if you go to high column density, you see that some of the points do intersect with that red box. But of course, you see many more points that also don't. So I think, you know, I mean, when you go to something like a protoplanetary disk, right? It depends on, do you have the core around it, for instance, that's going to attenuate things. In principle, what would be the better solution is to start with the diffuse or this kind of 10 minus 16 or so rate, and then try to estimate what you would expect the attenuation to be to your disk and use that. So some models will give you this 10 to the minus 17, some won't. So it depends on what you assume for your external spectrum.
And should we use a different base value for in a low mass star forming region versus like a cluster where there's more of these, rays forming from protostar accelerating because there's like 1,000 stars nearby versus one? What are your thoughts on that?
So I'll also note that most of the protoplanetary disk models that use cosmic rays only assume the external cosmic rays and don't assume cosmic rays accelerated through reconnection by the T-Tauri or just from nearby sources. Some, of course, do. I think ILSA actually had some models that had looked at this at some point, but I think Christian Raab has also done this. So there are some papers that have been doing this. I've been trying to guess the ionization, what the cosmic ionization rate should be for disks is. I think it's a bit of an open parameter space, but if anything, it should then just be treated as an open parameter space, not a single value.
But then you just turn it around. I mean, people observed the protostars and said, oh, the cosmic ray rate must be 10 to minus 15 or 10 to minus 13 or something. Are we not constraining it from chemical modeling of protoplanetary disks?
Not from prototype disk. So for instance, in this case, I mean, on the right, I mean, this isn't resolving the disk, right? So this is,
But there are people who model the disks, they assume
Yeah.
10 to minus 17. If they put in 10 to minus 15, surely there'd be some difference.
at least for the upper layers, it would almost for sure make a difference. I don't know if anyone has really done a lot of modeling though to actually push the ionization rates up that high, except Stella had a paper in 2019 with myself and John Holchip where we used UCL Chem to do this as kind of disks with like 1D disk models. And there it was using a higher ionization rate, but I don't know of other people who have done disk stuff where they really tried to push that external ionization rate above, 10 to the minus 15 or something, and then seeing what would happen.
Yeah,
But
John-
you will of course get attenuation then going into the disk.
Mhm.
So the disk surfaces will probably be the biggest ones that are impacted.
Ryan, you gonna say?
And just to follow up, people don't really try to constrain the cosmic ray ionization rate. There's only for a couple of papers and disks they've done it with observations of ions. It's still very area that needs to be looked at. We also need different ALMA observations to constrain that value better.
The ices as well, James Webb ice stuff.
Yeah, I mean, this is something where, I mean, with James Webb, it could be that, people will need to invoke cosmic rays to deal with, sputtering or non-thermal processing in disks. But who knows? I mean, most likely the biggest impact for the chemistry will be at the disk surface layers and not in the really dense coldest regions, because you'll already get a lot of attenuation just going into the disk.
And let me just follow up on the protostars and these very high ionization rates. I mean, is that accepted? Or, are there some, are all protostars at this elevated level, just some of them? I mean, what's going on here?
In terms of the kind of, from the theoretical modeling side, I'll say it is very difficult to try to make protostars unable to accelerate cosmic rays. Then there's the question of, okay, let's say the accelerated cosmic rays, say from near the surface, they then still have to get out. And that is then a much trickier question, because then they will typically travel along the magnetic fields. So one of Stella's PhD students, Margot Fitzaxon, did this modeling where she basically injected them at the protostar sink and then followed it out. And in that case, what ended up happening was a lot of the cosmic rays got basically funneled by the jet magnetic fields. And then basically you have the jets acting as basically particle beams in their source. There's some evidence that this might be the case. One of the sources where there's been a very high ionization rate, OMC2 FIR4, it's debated whether or not the jet from the FIR3 object is impacting it or not. If you look purely at the energetics, the impact shouldn't be enough to produce these ionization rates. But if there's, say, cosmic rays that are being funneled by that jet, then that might also work. So I think as people have measured towards more and more protostars and star-forming regions, they've seen enhancement. So on the far left from Jaime, the increase of the ionization rate is actually increasing towards this kind of group of stars up in the top right. So maybe this is, a signature that the star formation is increasing the ionization rate, or maybe there's something else going on with the chemistry that will lead to an inferring of the ionization rate. The best way that we can actually figure out if the robustness of these signals is by doing proper 3D cosmic ray astrochemistry models and then just testing the calibration methods. And this actually hasn't ever really been done.
My last note on the dominant, the synchrotron emission we do see it from some high mass protostars, synchrotron jets, but often we don't.
Yeah.
So maybe the synchrotron is something more direct to go after.
Yeah. So the synchrotron is, I think, probably the most robust. I mean, to actually try and do it from the accretion shock is probably not particularly viable, because you will need probably ridiculously high resolution to do that. But from jets, you see it quite a bit. But also too from H2 regions, right? Which H2 regions typically haven't been considered as cosmic ray sources. But you see synchrotron emission from H2 regions.
Wow. Do you?
Well, they're all fairly negative slopes, within the errors too. Except the top right. But the rest of them are pretty robustly negative synchrotron slopes. But
Could that be free?
they did modeling though and found that it was most likely synchrotron, and then there was a follow-up companion paper for Marco Padovani that did the theoretical calculus and then was able to kind of reproduce this. Again, making analytic assumptions of the particle acceleration and things like this.
Free from minus 0.1 around there, so what was it, minus 0.6 for synchrotron? Well, in solar radio, and we should look, there are famous synchrotron jets, and no one really knows why they're present in some sources and others. But maybe we can try and find out. Okay, we're going to wrap up soon. Any last questions for Brandt? Okay, if not, let's thank Brandt again. We know where to find you if we need. You're obviously the expert here on the cosmic rays, so very good. Thank you then. Thanks, Virginia. We'll see you guys later.